So last time we defined what radian measure was, and I'm going to show you two applications that involve or that use a radian measure. One is called finding the arc length on a circle, and the other one is called finding the area of a sector of a circle. And if you've already had high school geometry, you've probably learned those two things as well in that course, but you probably used angles measured in degrees and not in radians. So we're just going to simply modify those two formulas that you've probably seen already to handle degrees or to handle angle measure in radians rather than degrees. So last time we learned that angle measure in radians is defined by this ratio of arc length S divided by radius R. So imagine that we have a circle of some radius, and we simply said that this angle, if you were to measure that in radians, the number of radians is defined by S, which is this arc, length of that arc, divided by R, which is radius of the circle. So theta is equal to S divided by R. Well, now let's take that equation and cross multiply, thinking of theta over 1. And when we cross multiply, we get S is equal to R times theta. So there is a small formula for finding S, which is arc length. We simply take radius of the circle and multiply that by the angle in question, and the angle must be in radians. Must be in radians. So here are two examples. It says we have this circle that has a radius of 18.2 centimeters. Find the length of the arc intercepted by a central angle. And by the way, central angle means that the vertex of that angle is on the center of the circle, having each of the following measures. So A, they're giving you an angle that's already in radians. B, they're giving you an angle that's in degrees that you'd have to first change that to radians. So again, let's just draw a small picture, a diagram as to what's going on. We're told that the radius of this circle is 18.2 centimeters. And the angle in question ends up being 3/8 pi radians. So imagine this angle theta being 3 pi over 8, and we want to try to figure out what's that arc length, S. So part A, we know that S is equal to R times theta. So really all we got to do for part A is to take the radius, which is 18.2 centimeters, and multiply that by 3 pi over 8. Now when we take 18.2 times 3/8, 18.2 times 3/8. Don't worry about the pi quite yet. One correct answer would be 6.825 pi. That's a correct answer. And what would be the units of measurement here? We're still measuring a length, right? So since the radius was given in centimeters, we could say that this arc length, the distance from this point to this point on the circle, is 6.825 pi centimeters. Now, if the book specifically says, or your problem specifically says, please, round your answer off to the nearest whatever, that's kind of like the clue as to you have to change pi to 3.14 and multiply the two numbers together. So if I take this 6.825, and by the way, you do have a pi button on your calculator. It's the second button division key. So we can just say, take this previous answer times pi, and we get 21.44. 21.44 centimeters. So either one of those is a correct answer in this class. Just on multiple choice test questions, you'll see one or the other. Any discussion or questions there? So go ahead and try B. Try B. Angle that is intercepted is a 144 degree angle. All right, part B. Part B, the first thing that we will do is now since we're working with a 144 degree angle, that puts our angle over here, approximately over there somewhere. And now we'll try to figure out this arc length. And now the angle that we're given is 144 degrees. So 144 degrees, if you were to convert that to radians correctly, you should get 4 pi over 5. Any questions? The first part, 4 pi over 5. Now plug that into the formula. Arc length is equal to radius times angle in radians. Radius stays the same, 18.2 centimeters times 4 pi over 5. And your two correct answers, 14.56 pi. Or if you were to change pi and approximate, 45.74. And these would also be in centimeters. Do we do all right? So far, so good. A little easier than yesterday or last time, right? So far, I mean, it is. Okay, let's take a look at a real-world example using arc length. It says that Reno, Nevada is approximately due north of Los Angeles. It says that the latitude of Reno is 40 degrees north, meaning from the equator, while that of Los Angeles 34 degrees north. The radius of the Earth is approximately 6,400 kilometers. Find the north-south distance between these two cities. So they have that labeled for you. You need to simply, it's a very, very small piece of pie, but we are after that tiny little arc length between those two cities. So again, the first thing that I need to do is come up with the, what is the angle in radians. So we're traveling 40 degrees, and then we're only traveling 34 degrees, so that's a difference of 6 degrees, right? So the angle of that piece of pie, this guy in here, this tiny angle, would be 6 degrees. So the first step would be to take 6 degrees and convert that to radians. So we multiply 6 degrees by pi over 180, and we get pi over 30. So there's your angle measure in radians. Now to find the arc length.
Wouldn't it be the same as the 6,400 kilometers? Wouldn't it be the same all the way through since it's a radius?
Yeah, the radius is going to stay 6,400. Yeah, exactly. To find arc length, we'll take that radius, 6,400. Multiply that by our angle, pi over 30. And again, I'm going to give you two possible answers like the last two problems. You could say that that arc length is equal to 213.3 pi kilometers, or you could give me 670.2 kilometers. Distance between those two cities. Just kindly nod your head if you're okay with what you're seeing. Hannah? Yeah, okay. Another example, and I don't know if it shows up on your handout clearly or not, but the light blue segments are hard to see. So I'll make those stand out in a brighter color. Let me stop at the end of the wheel. So what we're being told is there's this drum or a gear or a wheel here that we're going to rotate this drum or this gear so many degrees, and we're saying we're assuming that the chain or the rope is the end of it was attached here where my cursor is. Now we're going to rotate that drum 39.72 degrees, which will cause the rope to start wrapping itself around the drum. So they want to know how much rope or chain has been used so far. So we simply want to figure out what is this arc length from that point to that point. So there's our S value that we're after. So this is identical to all the other problems. Since the angle given to me is in degrees, I have to first convert that to a radian measure. So we have 39.72 degrees, and we want to convert that to radians. So when you multiply that by pi over 180, 39.72, we're going to multiply that by pi over 180. .72, multiply that by pi over 80, pi over 180. We're looking at 0.6932, and you know, that would be our angle measure in radians. I'm going to leave all of that in the calculator, right? Because we're just going to turn around and multiply that by the radius of the circle. Radius of the circle is 0.8725 feet. So I'll just hit the multiplication button and say take previous answer times 0.8725. So our final answer in feet, 0.605 feet. 0.065 feet. There's our arc length.
Your crankweight ear.
It's my inner ear infection, right? Yeah, I just simply copied it off the calculator wrong. 605. 605. Thank you. That's about it for arc length. Oh no, I'm sorry, I got one more arc length problem. Yeah, this one's interesting, because we're gonna end up using the arc length formula 2 times within one problem. So the area that I have over here on the side, I want you to divide this workspace into two columns. Here we'll start talking about the small gear, and over here we'll talk about the large gear. So to give you a gist of what's going on, we have these 2 gears that meet at a common point, tangent point. What we're going to do is rotate the smaller gear so many degrees, which then causes the larger gear to turn, and we're going to try to figure out if I turn the small gear 225 degrees, that causes the larger gear to rotate by how many degrees. Okay? So starting with the small gear, let's figure out the distance, that point. If you were to imagine this point where the 2 gears touch, and now we rotate the smaller gear 225 degrees. Let's see how far that point that I identified moves. And that's the same thing as saying let's simply find the arc length. So we have S equals R theta. Again, we're going to have to convert your degree measure into a radian measure. So we're going to take, to find that arc length, radius of the small gear is 2.5. And we're going to multiply that by our radian measure, and our radian measure would be 225 times pi over 180. 225, that's our angle in degrees, and we're going to multiply that by pi over 180 to get our angle in radians. So now we'll just simply multiply that all together to get how far did this point move on the small gear. So 2.5 times 225 pi over 180. So I get 9.81, let's just make it 9.8175. 8175. Any questions there? Now that point that is also, you know, that point that I'm talking about is shared by technically both gears. So if that point is moving 9.8175 units on the small circle, it's also moving that same distance on the larger circle. So we're going to just simply carry this over to the next column, where now we're going to work the formula in reverse. What angle causes the big gear to have a arc length of 9.8175? So again, we'll start with S equals R theta. And in this case, we know S. S is 9.8175. And we also know the radius of the big gear, 4.8. So we have 4.8 theta. Now we'll divide both sides by 4.8. So theta is 9.8175, which I'm just going to, so I don't lose a bunch of accuracy, I'm actually going to keep the value that I currently have in my calculator. And let's take that value and simply divide that answer by 4.8. So there is our angle measure in radians, right? 2.04, that we can round off. 2.045 radians. Now, due to the fact that the first gear, they're giving you that angle measure in degrees, we should take what we have and convert it back to degrees. So we'll take 2.045, 2.045, and we're going to change it back to degrees. So we want to multiply that by 180 over pi. So we get 117.17 degrees. There's our solution. So by rotating the smaller gear 225 degrees, that causes the larger gear to rotate 117.17 degrees.
Go back. Can you click that calculator again?
Sure. Moving on. Told you that there were actually two applications to radian measure. One was arc length. Now the other one we call area of a sector. And simply what we mean by that is, again, you have some angle, some central angle. Vertex is on the center of the circle. You have some degree measure that will either be given to you in terms of, or some angle measure given to you in degrees or radians. And you're now going to be asked, what's the area of this piece of pie that's cut out? Now, when you were given this problem in high school geometry, the angle measure that you were given was probably always in degrees. So all you had to do was say, okay, let's just say I'm given a 30-degree angle. What you would do is say, well, what's the area of the whole circle? Area of the whole circle is pi r squared, right? You want a certain fraction of the whole circle. And how do you determine what that fraction is? It's your angle measure out of 360. So you would first say 30 out of 360, there's some fraction. You multiply that fraction by the area of the whole circle, and that gives you the area of that wedge or that piece of pie. That's how you did it when working with degree mode. Notice what happens when working with radian measure. Here again, there's the area of the whole circle, pi r squared. But now instead of it being some number of degrees out of 360, you now have some radian measure theta, and remember that 360 is the same as 2 pi. Well, look what happens. Your pi's cancel each other out. And you're left with 1/2 times radius squared times theta. So if the angle that you are given is already in radians, if not, you'll convert it to radians. You simply plug that value into this formula along with your R value, and that gives you the area of that wedge or that piece of pie. So let's go ahead and try this problem. It says find the area of the sector-shaped field. Crop circles and all that, right? And we're given a 15-degree angle, so we need to convert that to radians. So 15 times pi over 180, what's that become? Pi over 12, if you needed to know that. And now to get the actual area of the sector, we'll take 1/2 times the radius squared. Radius we're given in the problem, 321 meters. 321, so we'll square that. And then we'll multiply that by pi over 12. Get the calculator. Calculator, what is 1/2 0.5 times 321 squared times, and again, you can multiply it by 1/12, leave pi in the answer, or go ahead and convert pi to a decimal as well while you're doing all the computations. We'll just go ahead and throw in pi over 12, and we get 13,488 roughly. 13,488. What would be the units of measurement? Meters squared. Meters squared. Because of right here. Right here's where we're right there's where we're taking meters times meters, giving us meters squared. All right. Guys, okay with that example? Is that the last one? That was it.
Seems